Good morning. Welcome back again. So let's start the second part of chapter 6. You remember that every cell that we have, inside the cell we have lots of potassium, and outside the cell we have lots of sodium. Inside the cell we have fixed anion. An ion are negative charges. These are fixed because they never get out of the cell. Like what? Like phosphate in the case of ATP, like protein, majority of them they are negative, like DNA. Because of having phosphate, they are very negative. These are called fixed anion. Inside the cell, we have lots of negative charge ions. They are called fixed because they never get out. On the other hand, the other ions like calcium, like sodium, potassium, chloride, they may move in and out of the cell. So that's one thing. The second thing you have to understand is, here's my cell membrane. There are two layers of phospholipid, and these are the proteins. You remember from your biology or even from your anatomy that we have some protein that span width of cell membrane. They go from one side all the way to the other side. These are called integral protein. These are the protein that we talked about as a channel when the glucose or ions or water is going to come through. We have other type of protein that we call peripheral protein, and those are the protein that you found only in one side, either outside or inside. Integral protein is the one that they act like a channel or like gates. These ion channels allow molecules or ions which are water soluble to pass through. Therefore, they're selective based on the size and charge. For instance, if you have a protein that is lined with the negative charges, therefore the negative ions cannot go through this one because negative and negative are going to repel each other. If you have a protein that is lined by positive charges, then the negative ion is going to go through easily because negative and positive attract each other. Of course, the size is very important. If it's a large size, cannot go through this channel either. So therefore, we have two things to consider based on the size and based on the charge. Some of these ion channels are gated. They open and close, just like this one. As you can see, now it's closed, now it's open. So some of these channels are gated. It's called gated channels. They can open or close. And also I want you to know the word conductance. What does conductance mean? Conductance is about probability a channel is open or is closed. If there is a higher probability for a channel to be open, that means the higher chance for ions to go through. That means the conductance would be higher. When there's a less probability for a channel to be open, there's less conductance. That means less chance for ions or molecule to go through. It's all about probability. At any given time, what is the chance for a channel to be open and what's the chance for a channel to be closed? Now let's take a look at this cell. As you remember, we said some ions move in and out of the cell, but some ions are fixed inside. Why some of these ions they are more outside, some more inside? The position of these ions inside and outside depends on three things. One is the permeability of the membrane for this ion, how permeable the membrane is. The second reason is the pump. For instance, in the case of sodium-potassium pump is going to move the sodium out and bring potassium in. So that's another reason that ions they are in different side of cell membrane. And the third reason is the presence of these negative ions inside the cell. Those are going to attract positive ion in and it's going to repel negative ions out. So we said there are three reasons that these ions are not all in one side of the cell membrane. They have different distribution. Now, as you can see in this picture, the amount of sodium inside the cell is 12 and the amount of sodium outside is 145. Potassium is 150 inside and 5 outside. Chloride, with the same token, is less inside and more outside. And calcium is more outside, less inside. Calcium, chloride, and sodium majority outside, and potassium is the main one inside the cell. Also another one inside the cell would be magnesium. Bicarbonate, which is another important negative charge ion, is also outside the cell. Now, a cell is like a battery. Consider a battery when you buy from outside. It has two poles, positive and negative. If you look at inside the battery, there is a barrier. All the positive ions in one end and all negative ion is in another end. Now, if you attach a wire here, another wire here, and attach it to voltmeter, then you're going to see a number. it shows a voltage. What is the voltage? Is a difference of the charge in each pole. If you start using this battery, slowly this negative charge, this electron is going to go to the positive, and this battery is going to lose this difference of charges, and as a result battery is going to die and the voltage is going to show 0. With the same token, if I put the electrode inside and electrode outside the cell and attach it to a voltmeter, I'm going to see a number, just like a battery that you see 3 volt or 6 volt or 9 volt. Why is that? Because just like a battery, inside and outside the cell they have different distribution of ions. There are different ions inside versus outside. Therefore, we're going to see a number. The number is not going to be as big as 3 volt or 6 volt or 9 volt. It's very small. It's a millivolt. And as you can see in this cell, it shows minus 90 millivolts. Now you have to realize, as we have different size of battery, we have different size of the voltage in the cell also. Each cell has a different voltage. This happens to be a cells of muscle. A muscle cell usually have a voltage of minus 90. Let me make sure you understand what does it mean when you say minus 90. Inside the cell we have 90 millivolt less voltage compared to outside. In other words, this minus shows what's happening inside the cell. Hypothetically, if I say this is positive 90, that means inside the cell there's 90 millivolt higher voltage compared to outside the cell. So it's comparison of inside to outside. Inside the cell is more negative compared to outside the cell, we show minus. If inside the cell is more positive compared to outside the cell, we show it positive. It doesn't mean it's less than 0. It just means inside has 90 millivolt less voltage compared to outside the cell. We said some channels that are gated. These gated channels, they can open or can close, as you can see. But how are they going to open or close? Well, the answer is simple. Some gated channels open or close when the voltage of the cell change. That is called voltage gated channel. What does that mean? Let's say right now the voltage of this cell is minus 70 millivolts. Remember, each cell has a different voltage. This one is minus 70. Previous one was minus 90. If I change this voltage from minus 70 to minus 50, this gate opens. Some gates open when you change the voltage. That type of gate that opens due to change of voltage is called voltage gated. Some gates, they open or close if there is a chemical or ligand sit on the channel. So in this case, the channel is closed. If an appropriate ligand sits here, it's going to open the channel. Therefore, this channel opens because of the chemical. It's called ligand gated channel. An example for this voltage gated channel can be a sodium channel or potassium channel. So sodium channel or potassium channel, they are voltage gated channel. Let's talk about one of these gated channel. Let's talk about sodium gated channel, which is really important. In the case of sodium gated channel, we have 2 gates instead of 1. As you can see here, there's one gate here, and that's called activation gate. And there's another one is called inactivation gate. So we have activation gate, we have inactivation gate. You can close this channel using inactivation gate. You can close this channel using activation gate. But why this one is so important, I want you to know. Because activation gate is supposed to be a fast gate. It's going to close and open very quickly. Inactivation gate is a slow gate. It's going to open or close slowly. Before I go forward with next topic, I want to make sure one thing very clear. We talked about battery. We said the battery has a voltage. We talked about the cell has a voltage. However, in the case of cell, instead of calling it voltage, we call it membrane potential. We call it membrane potential. So we say, what's the membrane potential of the cell? Basically, I'm asking, what's the voltage of the cell? The membrane potential of the cell is, in this case, minus 90 millivolts. There's another term I want you to know, and that's called diffusion potential. Diffusion potential is a potential or voltage created by movement of ion. When the sodium moves down its concentration, when potassium moves down its concentration, when ions move down their concentration, they move from higher to lower, that they're going to create diffusion potential. Realize that diffusion potential only happens if ion can diffuse. If the ion cannot diffuse, then cannot create diffusion potential. It doesn't matter how much of that ion you have. If the ion is so concentrated in one area but cannot diffuse is not going to create diffusion potential. And the last thing I want you to understand is diffusion potential happens because of movement of a few ions that does not change the concentration of that ion. For instance, when the sodium moves from outside the cell to inside the cell, only a few of this sodium is going to come in that is not going to change the total amount of sodium in the extracellular space. In other words, the movement of sodium is not going to change the bulk amount of sodium that you had outside the cell. So I don't want you to think that by moving of sodium from outside to inside the cell, all of a sudden it's going to have, instead of 145 millimole, it's going to have 100 millimole. That is not going to happen. That few sodium comes in is enough to change the membrane potential without changing the concentration of the sodium itself outside the cell. Let me give you an example. We have lots of sodium chloride here. We have a small amount of sodium chloride here. And let's assume that this membrane only is permeable to sodium, but not chloride. So do you think chloride can create diffusion potential? The answer is no. Although we have a lot of chloride here, but because chloride cannot move, diffusion potential is not going to happen because of chloride. But because sodium can move, it's going to create diffusion potential. Sodium is going to move from this side of the container to this side. Let's say we have 1,000 sodium here, and we have 1,000 chloride here. And we have 100 sodium here and 100 chloride here. You may assume that we're going to bring the sodium here until this side and this side is going to have each 500 sodium, because then sodium is going to reach the equilibrium. But that's a mistake, because when the sodium starts moving to this side of the cell becomes more negative, because now you're losing positive. At one point, this negative charge becomes strong enough to tell the sodium, don't go to the other side, because now negative and positive are going to attract each other. So my point is this: although sodium can freely move from this side to this side, however, as soon as sodium starts moving, then the negative attraction here for sodium would be high enough that sodium wants to stay. So as a result, some of this sodium is going to come to here, but for sure not 400 of those. As a result, this side of the cell becomes slightly positive, and this side of the container becomes slightly negative. As you can see, the concentration of sodium, it didn't change. The bulk concentration will not change because the number of sodium that moves here and change the charge in each side of this membrane would be so small that does not change the bulk concentration of the sodium. So let's do an experiment. Remember, potassium is inside the cell majority, and some potassium is outside the cell. If you allow potassium to move freely, if potassium starts moving freely, what do you think is going to happen? Well, you may think potassium is going to move from inside the cell to outside the cell because of concentration. That is true. However, as soon as potassium is going to move out, inside the cell, which is very negative, is going to become even stronger negative charge. Now potassium has a mixed feeling. Should I go out or should I stay in? Potassium wants to go out because of concentration. Potassium wants to stay in because of the charge. As a result, very small potassium is going to move. Potassium is going to reach equilibrium. This equilibrium is not a concentration equilibrium, but is an electrochemical equilibrium. In other words, the force of concentration that's trying to push potassium out is equal to the force of the chemical attraction between negative and positive. When these two forces become equal, then potassium is going to stop moving. Let me repeat one more time. Potassium is going to deal with two different forces. A force of concentration that's trying to pull the potassium out, and the force of charges that's trying to keep potassium in. When these two forces become equal, then the potassium reaches equilibrium. That equilibrium is not because of concentration, is not equilibrium because of the electrical attraction either. It's an equilibrium between both forces. We call this one electrochemical equilibrium. Just like this example. Sodium is going to reach equilibrium, not because we have the same amount of sodium in each side of the cell, but because the force that's trying to pull sodium in this side and the electrical force that's trying to keep the sodium here become equal. Therefore, we call it electrochemical equilibrium. If you consider only potassium, if you consider a cell which has only potassium, no sodium, no chloride, no calcium, nothing, and you allow this potassium move, the membrane potential of this cell becomes minus 96. That means at minus 96 millivolt, potassium is going to reach its own equilibrium. If I do the same thing for sodium, this is a cell, and I have a lot of sodium outside. You have a small amount of sodium inside, and remember, inside the cell is what? More negative. If I allow this sodium to move in, what's going to happen? Well, now the sodium is positive ion, yes? So sodium is going to come in. Sodium now has two reasons to come in. One, because of concentration from higher to lower, and two, because inside is very negative. Sodium is going to keep coming inside the cell. And when the sodium reaches equilibrium, when I put an electrode inside and one electrode outside attached to voltmeter, I'm going to see a number of plus 60 millivolts. What does that mean? That means sodium is going to come in enough that inside the cell from minus 90 is going to change to minus 50, minus 40, minus 10, 0, plus 10, plus 40, and then it's going to get to plus 60, then it's going to stop. Now the sodium is in equilibrium. What type of equilibrium is that? Is it electrochemical equilibrium. Inside the cell become positive enough that now sodium doesn't want to come in anymore. So therefore we say the equilibrium for sodium is plus 60 and equilibrium for potassium is minus 96. Now I want you to think about this one. If you combine all the ions when the cell is at rest and I put the electrode inside and outside, you can see I get to minus 90. That means my membrane potential, the voltage of my cell, is very close to equilibrium of potassium. Why is that? Well, the answer is when it comes to considering all ions, the ion that has higher diffusion potential, the ion with the higher permeability is the one that bring the voltage of the cell or membrane potential of the cell close to itself. Since among these ions, potassium has a higher permeability, therefore the membrane potential of the cell overall is close to equilibrium of potassium. I'm going to repeat one more time. Membrane potential of the cell is closest to the ion with the highest permeability. Since among this ion, potassium has the highest permeability, the overall membrane potential of the cell is close to equilibrium of potassium. And that's an important point that I want you to understand. So far we learned that all cells have a charge. Inside, all cells are negative. Outside of all cells are positive. Majority of potassium inside the cell, majority of sodium is outside the cell. We said that when you let these ions move, there's going to be a diffusion potential. Ions start moving and create a voltage. We said overall, the membrane potential or voltage of the cell is close to the voltage caused by potassium. We call it potassium equilibrium potential. We said this equilibrium potential is due to two forces: concentration force that's trying to bring potassium out, and the electrical charge that's trying to keep potassium inside the cell, because inside the cell we have fixed an ion. So we said there are two forces applies to every ion. Now, is there any way, instead of doing the experiment, we can measure the equilibrium potential for any ion? In other words, can we figure out at which number the concentration and the electrical force will become equally strong that prevents movement of ion? Let me say one more time. Can we mathematically measure at what millivolt the force of concentration and the force of electrical would be equal so that potassium stop moving? The answer is yes, we can. Someone by the name of Nernst came up with this formula. It's called Nernst equation, and the equation would be minus 61 over z log of x from out, x of in. What does that mean? Well, z is the valence, number of charges. For instance, for sodium would be 1, for calcium would be 2. X would be the ions we are dealing with, let's say potassium or sodium. For instance, in the case of potassium, I can put 5 over 150. I won't ask you to calculate anything on the exam, but I want you to know the formula. I just want you to know what Nernst equation is. And the answer is Nernst equation is a formula that is going to tell you what would be the equilibrium for a specific ion when the concentration gradient and electrical gradient will become equal. Now let's go back to our cell. This is a cell, and it said when you consider all ions, my resting membrane potential right now is minus 90. Now, every cell has a voltage, every cell, or it's called membrane potential. However, there are only two cells that you can change this membrane potential. In other words, let's say a typical cell inside is negative and outside is positive. There are only two cells that you can reverse this one. That means you can make inside positive and outside negative. Those cells are called excitable cell. An excitable cell is a cell that you can excite them. You can reverse the charge. And those are either neurons or muscles. Let's say this is a muscle cell. This muscle cell has a membrane potential of minus 90. Since this cell is not excited yet, we call this one a resting membrane potential. A resting membrane potential is the voltage of the cell or membrane potential of the cell when the cell is not excited. When you excite the cell, of course, this number is going to change. This membrane potential is caused by diffusion potential. It's because of movement of these ions inside and outside the cell. And which of these ions has the biggest effect on the resting membrane potential? I hope you are thinking about an ion that has the highest permeability, and that is potassium. And also you have to understand, if for any reason the permeability of any of these ions changes, then the resting membrane potential is going to change. And that happens when you excite the cell. When the cell becomes excited, then the permeability of these ions is going to change. As a result, this number also is going to change. For instance, if you increase the permeability for chloride, then chloride is going to come inside the cell, and this number is going to become even more negative. Yes or no? If you increase the permeability for sodium, then more sodium is going to come inside the cell, and this number becomes more positive. For most cells, the resting membrane potential is between minus 65 to minus 85. For a neuron, it would be minus 70. And the last part of the discussion to finish chapter 6 is about chemical signaling. The idea is how cells they're going to talk to each other and interact with each other in your body. Well, the answer is we have 4 ways of communication between cells. One is when the cells are attached to each other by a gap junction, is a channel that is like a conduit and allows small molecules or ions to go from one cell to another cell. You have something like this in epithelial cells. You have something like this in the heart. If you remember, in the case of heart, we talked about intercalated disc. Intercalated disc is a junction between the cells. It's going to connect one cell to another cell. If something happens to this cell will know because there's a communication channel open between these two. That's one way of communication. The second way of communication is some cells, they release some chemicals that chemical is going to come out and is going to affect neighboring cells. That type of communication is called paracrine signaling. Another way of communication between different cells would be through nervous system. A neuron can bring information and tell the other cell what to do. For instance, you can move your finger, you can blink, or you can walk or stop walking. These are because of the order that comes from the neuron. That's called synaptic signaling. And finally, we can communicate between cells by releasing hormone. One cell can release a product, it's called hormone. The hormone is going to come to the blood and it's going to go to a distant organ and affect those cells. The difference between hormone and a paracrine would be paracrine only is going to affect the neighboring cells, is not going to go to the blood. However, the product of these cells, which is called hormone, is going to get to the blood and travel to a distant cells and affect them. And the last slide for this chapter would be how these hormones or chemicals affect another cell. Well, the answer is when this chemical, they're going to come to the target cell. So let's say this is a target cell. There are 2 ways of affecting these cells. One is if this chemical is fat soluble, it's going to pass through the cell membrane and it's going to sit on the receptor which is inside the cell. But if this chemical is not fat soluble, if it's water soluble, obviously it cannot get through the cell membrane. So the answer is you have to have a receptor on the cell membrane. So if the chemical is water soluble, it's going to sit on the receptor which is on the membrane, and if the chemical is fat soluble, it's going to pass through the cell membrane and it's going to sit on the receptor in the cell. In this case, because the chemical cannot come in, then we have to create a second messenger to bring this information in. If this is a first messenger and cannot come in itself, it's going to relay the information to someone else to give this message to the cell. Imagine that I go to the White House and I cannot see the president. I'm going to be the first messenger. I'm going to give my message, let's say the chief of staff, and chief of staff is going to take this information to the president. That would be a second messenger. Example, for this type of molecule that can pass through the cell membrane would be a steroid hormone. Steroid hormone is a hormone that comes from cholesterol. Anything comes from cholesterol is called a steroid hormone. So steroid hormone is a hormone that can pass through the cell membrane. Thyroid hormone also can pass through the cell membrane. Nitric oxide, NO, also can pass through the cell membrane. These are fat-soluble examples. And if cannot go through the cell membrane, like insulin, then it's going to sit on this receptor and it's going to use a second messenger. The most common second messenger is called CAMP or cyclic AMP. Cyclic AMP is derived from ATP. That is going to bring us to the end of this chapter. I hope you enjoyed it. I'm going to come up with a new set of recording for chapter 7 very shortly.